Okay guys, so let's get started today. Today our topic of discussion is eccentrically loaded columns. So you guys have already done analysis of columns and in your MOSII 1, Mechanics of Solid 1, where you were introduced to simple formula like stress is equal to P by A, okay, to solve compression problems. And then when you kept on increasing the length, you faced a circumstance where the compression member started buckling, and then you got introduced to Euler buckling. Okay, you derived the Euler buckling equation law. So the example, if I can give you, imagine I've got this member, and this member is under compression. Okay, so if I apply load onto it, there is possibility that it doesn't buckle. Okay, buckling means like it won't go out of the way, it will actually crush. If I keep on increasing the load, it will crush. Okay, the example of buckling is like if I've got a member like this. In this case, when I apply the load, it doesn't get crushed, it buckles, it bulges out. This is the buckling. Okay, this is what's called buckling. So what happens is that if you go for a stiffer member, which means whose area of cross section is bigger as compared to the length of the member, then there is a possibility that it will actually crush. So it won't buckle. In other words, it won't bulge out. In this case also there is a possibility that it bulges out, but if I chop it off and I make the length smaller, then there is less possibility of it bulging out. So actually what we are looking into is the geometric dimension of the structure. Geometric dimension means the area of a cross section and the length. If the area of the cross section, okay, the dimension of the area is bigger or bigger than the length of the member, or in other words, it's of a reasonable proportion to the length of the member, then your member would crush rather than buckle. If the dimension of the cross section is very small as compared to the length of the member, then there is a possibility of that compression member getting buckled. Okay, so I'm just making my statements generic. Why? Because we quantify it. We know, we find out exactly where the cross section will buckle and where the cross section will crush. Okay, we know exactly the formulas. But in general, I mean, like to make comments, just to make a conceptual understanding, we can appreciate that if the dimension of cross section is of a significant proportion as compared to the length, then there is a possibility of that member getting crushed rather than buckled. Okay, so look at this member. This member, look at the cross section of this member. This member has got a significant cross section, and this cross section is, say, around about almost two times the longer. The length of this member is almost 2 times the biggest dimension of your area. Okay, so the area dimension, which is this one, okay, the length, that is, if you add it twice, so then you might get the length of this member. That's why, I mean, so we can say that the length is actually twice of that, the bigger dimension of the cross section. So that's why when I apply the load, okay, apply the load, so it doesn't buckle. Okay, although it can buckle. Why? Because since still we have got a bigger length, but I mean like under normal loading, like normal loading by a person, by an able-bodied person, it's not buckling. But if we, on the other hand, look into the example of a paper also has got dimension. Its longer dimension, okay, is almost say 1.5 times, okay, the height of this paper. But this is very easy to buckle. Okay, this is very easy to buckle. So what's going on in this member whose dimension is, or whose length, wise dimension, whose length is almost twice that of this dimension, still when I apply load on it, it doesn't buckle. And in the case of paper, although the dimension of the area dimension is almost say 1.5 times the length, but I apply a very little load and it buckles. What is the reason? The reason is the second dimension, which is the width. Area is made up of two dimensions. Okay, area is made up of two dimensions. So one you call width, one you call depth. Okay, so in other words, what I mean to say is that if I have got an area, this area will have width and this will have depth. Area is always made up of two dimensions. Okay, and then we have got a third dimension, which is the length. Okay, so there is a third dimension, which is the length. Okay, these three is the game between all these three dimensions. When will a structure, when will a compression member, and remember that this is always under compression. So when will a compression member buckle or not? That is a function of three dimensions, which is the depth, width and the length of the member. Now I give you example of a paper and an eraser. Eraser is a bit more challenging to buckle and paper is easier to buckle. The reason is that in the case of paper, this W is very small. Okay, so because this W is very small, okay, that's why it buckles easily. And please notice that a thinner member will buckle in the direction of your smaller, dimension. So this is your smaller, so you have got the length and you have got the thickness, and it is getting buckled in the direction of thickness. Okay, it is getting buckled in the direction of thickness. So if you have got two dimensions and if I keep on reducing one of the dimension, okay, as compared to the length, the structure, okay, or the compression member will buckle, okay, and it will be, and buckling is always out of the plane, okay, but it is in the direction or in the outward drawn. Okay, so if I keep on reducing this W, what will happen? It will buckle out of the plane like this. So now, why is it buckling out of the plane? Why is it not buckling in this direction? Because of the moment of inertia. This is a function of moment of inertia. Moment of inertia, I is equal to BH cubed by 12. Okay, so that direction which will give us the least moment of inertia, that direction is most critical. Okay, so you see, in this case we have I is equal to d w cubed by 12 and I is equal to w d cubed by 12. So the moment of inertia, the critical moment of inertia is dw cubed by 12. Okay, so it will, so when I say in the direction of the least dimension, what I mean to say is that it will buckle in the direction of least moment of inertia. Okay, so please see, I'm tying up my argument. Okay, so what I'm saying is that if we keep on reducing one of the dimension of a member, okay, one of the cross section, the one which is having least, the direction which is having least moment of inertia, that direction would be susceptible, would start becoming susceptible to buckling. Yeah, so that is an important consideration in case of columns. So what we say is, if we keep on making it stiffer, or in other words, if we keep on increasing both the dimensions, okay, so what we are doing essentially is we are reducing the buckling, okay, the susceptibility to buckling, we are reducing that, and we are pushing the structure to fail in compression, okay, or in crushing. Just like you put a cube in between the platens of UTM and you apply the load, what happens? It crushes. The concrete cube crushes. Why? Because it is not susceptible to buckling. Okay? So that's the same. So this was just a refresher about buckling. Now this figure is familiar to you. This figure is telling us it's drawn between the critical load, which is FCR. Okay, so this is the critical buckling, FCR is critical buckling stress, and the slenderness ratio, which is LE by R. Okay, as I told you that the buckling is actually function of three things: length and both the dimensions. Okay, so we combine both the dimensions in a form of R, and R is actually I by A. So it's a mathematical term which is equal to I by A. So we have area and we have moment of inertia both lumped into one parameter, which is radius of gyration. Okay, so radius of gyration is a function of moment of inertia. Okay, so that's how by using R we are actually incorporating these two dimensions. Okay, so LE by R, that is your that's slenderness ratio. If your length, if you keep on increasing your length as compared to R, which is a function of moment of inertia, in other words, if you keep on reducing your moment of inertia, okay, so from this demonstration I told you that what happens is that we are making the column or a compression member more susceptible to buckling, and our column is becoming longer and longer. Okay, so it's becoming longer and longer. You did in your MOSII 1 how to work out the critical stress in a column which is long, and that is by using the famous Euler buckling equation. Okay, Euler buckling equation is used to find out your stresses in the column. Okay, for long column. please notice that this area where the buckling takes place, that is called elastic region. Why elastic region? Because actually the stress level is within the elastic. You are not. So what I am saying is that normally you have got stress strain diagram. Okay, and this region is actually your elastic region. So you have just applied the load. Okay, the structure material wise is still elastic, but it buckles. Like look at this one. This page hasn't deformed. I just slightly apply the load and it buckles. So the reason is that the load is still in the elastic range, but it buckles. Okay, so that's why I've written elastic buckling. This diagram is drawn for steel structure. Okay, so a steel structure has got, we have got a long column region. Then we have so you have got a very long column, okay, which means that its length is significantly higher than the dimension, the area, okay, both the area dimension. So it's significantly higher. Then what happens is that if we keep on reducing the length of the column, we reach a stage where we have got buckling intermediate, which is called intermediate range. In this range, you can have partial buckling and partial crushing. Okay, so the column, so initially when you have elastic buckling, now I start increasing, say, the dimension, the thickness. Okay, I keep on increasing it, so a stage will come that my column will be buckling and at the same time it will be crushing. In other words, the stress will be somewhere non-linear. It would cross this point, it would be somewhere in this range, and at that point it will buckle. Okay, that is called intermediate range. Now, from this range, if I further reduce it, what happens? I come to a point where there won't be any buckling, okay, and my compression member will be failing only in compression, okay, in crushing, no buckling at all. So the same paper, I start increasing the thickness, okay, so the thickness is increased extensively, okay, so imagine I stack papers with this, okay, and you get a pack of papers. Then you apply the load, it won't buckle like this, okay, it will just crush. If you apply the load, it will crush. So you are then in the short column range. So these are the three important ranges which is specified. The black line is the one which gives you whether you are in elastic, inelastic, or the short column range. Now there are two things which happen in the case of columns, because of which you don't follow the black curve. One thing, two issues pushes this curve down, okay, which I have shown in red. And what are they? One is residual stresses. That means that there are internal stresses inside your steel structure. Okay, internal. For example, when the steel is when you put molten steel, okay, in your molds, and then it starts cooling, allow it to cool. Okay, this is just like if you are baking something. Baking, what happens in baking? For example, you are baking a cake. Okay, so first of all, you put all the ingredients, then you put it in the oven, and then you set the oven temperature. Then your things start baking, what happens? That initially all your ingredients will start melting, isn't it? Everything starts melting and everything gets mixed. Okay, it's that melting. What does that melting do? It mixes all the ingredient. Then you take the cake out and leave it for some time outside, and then it becomes a hard cake. That's what happens. So similar thing happens in case of steel. In steel also, you put your steel initially is in molten state, then you bring it out from oven and you allow it to cool down. Okay, in different shapes, I shapes, L shapes, whatever shapes, but in that sort of mold it's placed and you allow it to cool. So when it's cooling down, it's not possible to cool it uniformly everywhere, that it cools down uniformly everywhere. Some points get cooled down more as compared to other points. Okay, like for example, when I switch on AC, okay, and I suddenly come inside, okay, I'm outside, this room is very cold, okay, and I step in the room suddenly, okay, so what will happen? Suddenly, not all my body parts will acquire the temperature of the room, okay, some part will, all parts of my body will be at different temperature, okay, and then with the process of time, what will happen? My body will acquire the temperature of the room. Do you agree with that? Yes? If it's a very cold room, I come from a very hot weather, suddenly I step inside the room, not at once all parts of my body will acquire the room temperature, okay, the cold room temperature. Different parts will acquire different temperature, and the reason is that some part of my body are covered more, some part are exposed, some parts some parts are on top of another. Like for example, my sleeves are up, so they are more exposed to the cold as compared to the rest of my body, isn't it? So the same thing, so I acquire different temperature. In steel also, that's what happens. Steel acquires different temperature. As a result, there are different stresses induced inside steel. Okay, and that's why, so that is one of the reasons. When you allow the steel to cool down, it's not like body that it will acquire the same temperature later. Those stresses get embedded in steel. Okay, different parts become cold, and though that differential temperature that gets embedded in steel, and the steel becomes stressed. Okay, so that is one thing which is called residual stresses. That's very common in steel and other elements of the same type. So that is one thing because of which we don't follow this